Before I pass out the quiz today, you'll need to make sure you turned in those 3 assignments listed under bell work, and you need your phones and smartwatches put away. So please try to get all that done during the minute of silence here.
Good morning, FHS. Today is Monday, 4, 33. Please join me in silence. Please stand if you are able and join me in the pledge. I pledge allegiance to the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
All right, reminder that our quiz this morning is no calculator.
Thank you and have a great day.
All right, can't remember how many points this one's worth, but it does look like each question has the point values on there, so I guess you can add those up if that is important to you. And you should be using about half a class on this. There are a few handouts I need you guys to pick up when you're done with your quiz. I didn't lay them out on our table this morning just because it is several handouts, and I know that they're in the way when you're putting in. So when you guys pick up your phones, just also pick up your handouts.
you.
Okay, I think I've got all of our quizzes this morning, so a couple things here. If you forgot to pick up your phone, please get that, and if you forgot to go get the handouts, please go get those. Again, I did not put the handouts out until after you started the quiz, so I just thought that might be easier for you. All right, we've got just one more new section, or new to us section, before spring break comes around. You guys know we have all of this week and all of next week till spring break. So we're going to cover section 3.2, quiz it the second half of next class, have some time for test review so that you can review 1.9, 3.1, and 3.2, and then get in the test before spring break. So I think that'll leave us one extra day before spring break, but somehow A-Day just had one more day than B-Days. So I guess if anything, then that should be helpful. Okay, so the numbering here, to start off, 94 is going to be the one-paged one that looks like this. Now, I guess the word of caution I need to give to you is this is where we are going to start talking about logarithms. In this section, we only talk about graphing logarithms and properties of logarithms, but you need to be forewarned that when we come back from spring break, we will do another 50-point unit over sections 3.3 and 3.4, which are also about logarithms. So our properties that we will be talking about and a little bit of the graphing we'll be talking about will carry over for the first couple weeks when we return to. So, all right, the first thing you need to know about logarithms, and specifically what's going to help you with the graphing, is knowing that they are inverses of exponential functions. So 3 to the x is inverses with log base 3 to the x. Those are inverses of each other. The inverse of 5 to the x, we will ask you questions like this, would be log base 5 to the x. Or going the other direction, the inverse of log base 2 to the x would be 2 to the x. So you need to know which exponential function is inverses with which logarithmic function. Now, the way that that's supposed to help you, and the whole purpose that we did section 1.9 for a couple classes, is ultimately I need you to be able to graph something like this equation without a calculator. Negative log base 3 of x plus 5 minus 1. So I can show you how to do that, but again, you have to have this part memorized. Actually, we'll aim for this one first. That will be for the second graph. So if you want to know what log base 2 of x plus 3 looks like, you really should start off with 2 to the x. 2 to the x is an exponential function that you should be familiar with after we reviewed it recently. The reason 2 to the x is supposed to be helpful is that he is inverses with log base 2 to the x. So I could take a point on 2 to the x, switch x and y, and I've got a point on his inverse. 1, 2 becomes 2, 1, 2, 4 becomes 4, 2, 3, 8 becomes 8, 3. You can switch x and y on as many points as you would like to. I'm not going to keep this up here, but notice there's the line of symmetry at y equals x that we expect to be there when they're inverses. And honestly, that's the easiest way to know what log base 2 of x looks like. Now, very likely, our couple of weeks before spring break and our couple of weeks after spring break, you may memorize that a logarithmic graph basically looks like this. Just like 2 to the x and 3 to the x and 5 to the x and e to the x all look the same. Log base 2 to the x, log base 3 to the x, log base e to the x, log base 5 to the x all basically look the same. They change a little bit in how quickly they grow, but the general shape of the graph is the same. Now, if I wanted to graph this one, we would just need to finish off with our exponent rules. This would be, or transformation rules, sorry. Shift it left 3. So you can just take all these points you were sure about, shift them left 3, replot them, and even this vertical asymptote. There is a vertical asymptote at x equals 0. So if you shift it left 3, now it's at x equals -3. So you already know your transformation rules, and you know what it means to be an inverse function, and you should be able to graph 2 to the x. You just have to see how these pieces fit together so that you can graph something like this without a calculator. Graph this so you can switch x and y and graph as inverse, and then if you know what this looks like, you can just apply transformation rules to it. So in the end, see, I've got more than one graph here, so I really should label which one I'm calling h of x. Okay, the next one doesn't have the lead-up questions to it, but I would approach it the same way. This is far too complicated for me to go straight to what this graph looks like. But at its core, it's log base 3 to the x. So personally, I would graph as inverse 3 to the x. 3 to the 0, 3 to the first, 3 squared. Write all of that out in the table if you want to. But you should know what 3 to the x generally looks like. The reason you should start with that is he is the inverse of log base 3 to the x. So every point you know about 3 to the x should be a gimme point on log base 3 to the x. 0, 1 becomes 1, 0, 1, 3 becomes 3, 1, 2, 9 becomes 9, 2. The horizontal asymptote of y equals 0 becomes a vertical asymptote of x equals 0. Then I can just worry about transformations. So if I plug the number in for x, the first thing I would do is the plus 5. So that's going to shift it left 5. So 1, 2, 3, 4, 5. 3, 4, 5. Now, you don't have to do this, but to me my graph gets a little bit busy, so I'm going to erase some of these prior steps. They're helping me, but now they're just kind of in the way. Okay, the next transformation would be this negative out front. Multiplying a parent function by a negative is going to flip it over the x-axis. So anything on the x-axis will still be on the x-axis, but this point will flip over, this point will flip over, and again, I'm going to just erase the previous step just to reduce confusion. And then finally, to graph I of x, the last thing is this -1, which would shift it down 1. So there's been a couple points here that I've been sure about the whole time. So I can just shift those points down 1. And that is a reasonably easy way to figure out what a function like that looks like. Of course, most of these functions don't have that many transformations, but even if it did, you can still do it in steps. So again, I graphed 3 to the x because I knew what that looked like. Took the points that I was sure about, switched x and y, and got us inverse, log base 3 to the x. And then because of this, I shifted it left 5. Because of this, I flipped it over the x-axis. And because of this, I shifted it down 1. And I just did that one step at a time to do that as carefully and accurately as I could. Okay, so we may ask some questions about the graph. So something like domain, we can see he approaches -5 on the left and goes forever to the right. Of course, your graph has to be correct for you to be able to see that. The x-intercept, depending on how accurate your graph is, you might think it's at -4, but I think it's a little bit less than that. So the same way that hopefully you did well, I guess on your quiz it kind of landed on a nice whole number if I remember right, but you can do this algebraically. So x-intercepts always have a y value of 0. Now, to solve this, we do have to kind of know a couple properties here, so we'll talk more about that on the other worksheet, but we'll just go ahead and do this together real quick. You could add the 1 and multiply both sides by a negative to get to here. This is completely optional, but I'm going to switch to left and the right side because I think it's easier for y'all to see what I'm going to do next. This is referred to as logarithmic form. This is one of the first things we'll talk about on the next handout. You need to know how to switch that to exponential form. And basically, to take it out of logarithmic form, you're going to remove log, but for you to do that, there's two things that have to switch place. It's going to be the -1 and the x plus 5. So x is -5 plus 1/3. Of course, we could add that together if we really needed to, but it makes sense. It's close to -5, but a little further to the right. So, but all I really want you to get out of that at this point is don't just eyeball it from your graph. It's not -4.5. It's not -4. Just plug in 0 for y and solve. The solving we'll practice on the next handout. Okay, and then the vertical asymptote. So a logarithmic graph started off like this. So if there's no transformation, the vertical asymptote would be x equals 0. But then we shifted it left 5, which moved it to x equals -5. We flipped it over the x-axis, which doesn't change where this vertical asymptote is, and we shifted it down 1, which doesn't change where this vertical asymptote is. The vertical spike in the graph that your graph never crosses is x equals -5. So those type of questions, you guys have been answering domain, range, asymptotes, increasing, decreasing, stuff like that for a long time. Transformation part you've also been doing for a long time. The most important part of this handout to help you get your feet on the ground is use what you know about exponential functions to give you some points on a logarithmic graph. Knowing a few points on an exponential function by default should give you a few points on a logarithmic graph. Okay, anything specific about that one that jumps out at you that you'd like to clear up before we go on to 85 or 95? Okay. So again, the numbering of these is a little bit weird, but 95 is the one that will be 2 pages that starts off this way. So this one's going to not focus on the graphing, but we'll focus on the properties. And again, not only do you want to know these properties to do well for this quiz and the next test, but the test after that as well. The stuff after spring break will go smoother the better you understand these properties. Okay, and the first thing I need you to convince you of is why we even need logarithmic functions. So, if I ask you to solve something like this, 2 to what power gives you 4, you should be able to do that in your head. Or 2 to what power gives you 5, well, that's a little bit harder. This is a nice whole number. This is not a nice whole number. So, the whole point of logarithms and logarithmic functions is so that we can solve exponential functions. If you need to solve for a variable in the exponent, the only algebra trick that you have is logarithms. So we'll come back to this one in just a second after we talk about a few of these. So one skill you need to have, and this is what I started to do on the other page that I said we would talk about on this page, is switch between the two forms. These are in exponential form, and we want to trade them into their equivalent logarithmic form. So they will be saying the same thing, but they will look different. Well, logarithmic form is going to have the word log in it. But to move this to logarithmic form, you have to switch two things around. So it would be the 2 and the 9. So 3 squared equals 9 is the same thing as log base 3. This becomes your base of 9 equals 2, because the 2 and the 9 switches place. On this one, you would switch b and c. So this would end up being log base a of c equals b. On this one, you're going to switch the 2 and the 16 and leave you with log base 4 of 16 equals 2. And this one, you would switch the x and the 5 to leave you log base 2 of 5 equals x. So to go from exponential form to logarithmic form, you just throw the word log out front and you swap the place of 2 of the numbers. You just have to know which 2 that they are. Now, going back to this question, this is the easiest and probably most common way. Unfortunately, it probably shows up on the ACT too. I say unfortunate because I wish we had gotten to it before y'all did the ACT in school the other day, but it is what it is. But sometimes if you solve in an exponential, all you have to do to answer this is switch the forms. This is in exponential form. If I switched it to logarithmic form, I have the answer, because here is what x equals. Log base 2 of 5. Now, that's some weird decimal, which is why we couldn't do that in our head. And I will talk about how to put this in the calculator in a bit. It's called change of base formula, but it's about 2.312 approximately, which makes sense. 2 squared would only be 4, and 2 to the third would be 8. So our answer has to be somewhere between 2 and 3. But simply knowing how to switch from exponential form to logarithmic form was the one and only step to solve that equation. Now, on the last handout, on the graphing thing, I did it the other direction. So you also need to be able to go from logarithmic back to exponential. So it's just undoing. If you really can do this skill is just the opposite of that. You want the log to go away because you don't want it to be in logarithmic form. But for that to happen, you have to switch these two things back to how they were. So 3 squared equals x, a to the b equals c, 8 to the x equals 11, 2 squared equals 4. I don't think it was y'all, but one of my classes talked about the ACT, and I'm pretty sure this was one of the things they asked on there. Was trying to get you to switch the forms. So. Okay, there are 2 times, specifically when you're looking at your calculator. Right here, your calculator has 2 buttons dedicated to logarithms. And when you hit the log button, notice it does not put a base down here. And if you hit the LN button, which stands for natural log, it doesn't put a base here. These are the 2 that you use a lot. The fact that your calculator gives you an entire button for them is a big hint there. But if you're using those, it's expected that you know what these bases are. So natural log, I don't know why it's LN, but it's for natural log, is really just log base e. That same number e that happens to show up in compound interest formulas. So anytime you see a natural log question, until you feel more comfortable, or maybe for the rest of your math career, it never hurts you to just take one step and change natural log into log base e. That's all natural log means. If the base is not written there, like what happens when you just hit the log button on your calculator, it's an understood base 10. So same thing, until you feel comfortable with that, you should probably just write a 10 in there. Just like when we say x, it's an understood 1x. Logarithms, if there's no base, it's an understood base 10. All right, one of the things you need to be able to do is evaluate some logarithms without a calculator, and they have to be fairly reasonably easy to work out, but let me say, give you a couple strategies here. The first, I think, relates the first page of stuff, but maybe not the most efficient. So let's say I ask you to work this out on the quiz. What you could do is you could say, well, let me set it equal to x and I will solve for x. One way you can do that is you could switch the forms. It's currently in logarithmic form. Switch this 7 and this x, make the log go away, and now it's in exponential form. And the thing about exponential form is you're just a little more familiar with it. You're a little more likely to look at that and be able to see what the answer is. Okay, same thing with this one. There's no base written here, so that's understood base 10. Feel free to set it equal to x. Switch the forms. Switch it from logarithmic form to exponential form. And when you phrase it this way, if it's one we're expecting to do without a calculator, it's not going to be some insane weird decimal. It's going to be, it could be a fraction, but most of the time it's going to be a nice whole number. That's the long way to do it. The short way, and how most people that are familiar with logarithms do, is they just phrase it a certain way in their head. So that's what I'm going to do on the rest of these. This is really just saying 7 to what power gives you this. This is saying 10 to what power gives you 100. Not what is times, but what power. This is saying 10 to what power gives you 10. This is saying 10 to what power gives you 1. Anything to the 0 power gives you 1. This is saying 3 to what power gives you 27. Not 9, because it's not multiplication. 3 to the third. 3 times 3 times 3 is 27. This is saying e to what power gives you e. This is saying e to what power gives you 1. Well, anything to the 0 power gives you 1. And this is asking 2 to what power gives you a half. Now this one, it's a little harder because you have to use exponent rules. 2 to the first gives you 2. 2 to the negative 1 is the same thing as 1 over 2 to the positive 1. So 2 to the negative 1 is what would give you 1/2. But if you phrase it that way in your head, again, you have to be careful not to use multiplication, but you don't really have to switch the forms every single time. But switching the forms is just kind of a visual of how you should phrase it in your head. Anything to the 0 power is 1. Those are very common questions. Anything to the first gives you itself. When there's not a base 10 there, you might want to write in a base 10. If it's natural log, you might want to rewrite it to say log base e. E to the first gives you 1. Okay, I mentioned this a second ago. There is a thing called the change of base formula, which honestly with newer calculators is almost not important. However, I do know there's one thing in calculus for you to understand why it works, you have to know change of base, and in college algebra they still will quiz and test you on change of base, so it's good for you guys to know this. So if you go to type this in your calculator, if you want to get this decimal or this as a decimal, you got to know how to be able to type this in. So if you go to your calculator and you try to hit the log button, it doesn't let you go in there and change the base to be 3. So there's got to be a way to do that. So change a base just says, well, you can change these to base 10s if you write it this way. You could do log base 10 of 7 over log base 10 of 3. Or if you'd rather use natural logs, you can do that too. Natural log of 7 over natural log of 3. It doesn't matter what the base is, it's just got to be the same base in the numerator and the denominator. These are the two that you are likely to see because these are the two that have been programmed into your calculator. So if I want to know what log base 3 of 7 is, again, I can do log of 7 over log of 3, enter, or natural log of 7 over natural log of 3, enter. We often put a multiple choice question on our tests like this, so you do have to know both ways, but that's about 1.771. 1.771. So for this one, if I only care about an estimate, I can guesstimate. I know 5 squared is 25, so the answer to this is a little bit bigger than 2. But if I need to be more accurate than that, I would need change of base. So I could do log of 27 over log of 5, and or natural log of 27 over natural log of 5. And I will type it in both ways just to let you see that it is in fact the same thing both directions. 2.048. 2.048. Okay, so I started off saying that change of base is kind of becoming obsolete, and in some ways I'm kind of surprised that we still teach it. But again, a large reason why we still teach it is because it's very likely you take college algebra someday and you're going to have a test that asks you about change of base. So that's why we hold you to it too. But for 30 seconds here, I will show you there is a way to do this in your calculator as long as you have a TI-84 and it has been updated anytime in the near future. But there's a special menu that they started adding to these that does not exist in the 83s. If you hit alpha window, it pulls up some different stuff. It's a quick place for absolute value. If you're doing calculus next year, you'll use 3 and 4 a lot for derivatives and integration. But specifically, choice number 5, if you do that, it does let you type in the base, the way it looks. So if I want to know log base 3 of 7, this actually lets me put in a 3 where it looks like the base is. So again, I'm not going to keep repeating that because it's a little bit of a shortcut and it's fine for you to know, but you still need to know change of base. So alpha window, option 5, log base, and then you can type it in the way it looks. I would caution you from doing that too much though, because then you won't practice change of base and we will quiz you on that. Alright, probably the most important property in logarithms. So there's a couple random properties we need to talk about, but this one is the real important one. And I've got an example. That's just a double. I've got an example to show you how this is going to be useful, even though we're not going to use this too much right now. And this log property says that if you have an exponent, like c, on something that you're taking the log of, that exponent can come down out front. That is the only algebra trick that you will ever learn to get an exponent, or to get a variable out of the exponent, like that. How that is going to help us, again, not so much in this section, but when we're all said and done with logarithms, is in an equation, you can take the log of both sides if you want to. Usually in calculus we do the natural log of both sides, but really you could do either type of log. But if I took the log of both sides, now this fits this property. X plus 2 is an exponent on something I'm taking a log of. So this x that I'm trying to solve for can come down out front, natural log of 4 is kind of nasty looking, but it's just a number. We could distribute that, and then this is just a number. We could subtract it over. And then divide both sides by natural log of 4. So nothing that you would ever guess. Natural log of 6 minus 2 natural log of 2 all over natural log of 4. But really the only fancy algebra thing that I did there was take the log of both sides so that this property applies. Exponent on something you're taking the log of, 99% of the time you bring that exponent down. Sometimes in calculus, and a little bit for you guys, you'll actually bring the exponent up. You can go either direction. Again, you don't need to stress about this part right now. Obviously you should have it down on your notes, but I'm just showing you why it's important. Okay, another property that's pretty important, and this one came up a lot last week in my calculus class. Again, I'm going to tell you what the property is, and I'm going to show you why it's important. The why it's important isn't going to apply to you guys, but I just hate saying you have to know this, so without any context. But one log property says that if you have a number like a, and his exponent is log base same number a of something, all of that just simplifies to something. So like if it was log base 3 of 5, it would be 5. If it was 8, log base 8 of 72, it's going to be 72. For your sake, you only have to recognize the pattern and know how it simplifies. But again, just to give you some context and why we insist that you do this, the way this gets used in calculus is there is a fancy algebra trick where if you have to solve for y equals, and again, if you guys have any friends in calculus, you can ask them. They just did this last week a lot. But this isn't natural log times y. You can't just divide both sides by natural log. It's natural log of y. So we have to use this fancy algebra trick where it's called exponentiating. We make both sides of the equation an exponent of e. And since we're doing that to both sides, it's considered to be balanced. But the reason why we do that is because then this guy is this property. This is e to the log base e of some stuff. So all of that just simplifies to the stuff. And so when we're trying to figure out what y is equal to, that's the only way to do that. Exponentiate both sides and then use this property. I think we will ask you to try exponentiating on a question or two total in this course. But again, I'm really just showing you to try to emphasize why this is going to be important to you at some point. Okay, so some more log stuff, but nothing new. It's just that you will have to apply some exponent rules sometimes. Also, when we come back from spring break, I can give you an option on how to work these. But right now, the only way to work these would be to rewrite with exponent rules. 10 to the 5th in the denominator is the same thing as 10 to the negative 5th in the numerator. 99 times out of 100, you move a negative exponent to the other side of the fraction and make it positive. But in this case, we want to go the other direction, because now we've got an exponent on something we're taking the log of, so the exponent can come down out front. And then we can simplify this. There's no base written here, so if it makes you feel better, put in a base 10. But this is really just 1. This is saying 10 to what power gives you 10. So negative 5 times 1 gives you your answer. Okay, same trick here. Bring this e to the 7th up and make it e to the negative 7th. So now the negative 7 is an exponent on something you're taking the log of, so that negative 7 can come down out front. And natural log of e is just 1, because natural log means log base e. So this is saying e to what power gives you e. So your answer comes from negative 7 times 1. Okay, I think this will come up on the next worksheet, but if there's more than one term, you need to make sure that both are negative. If you're going to bring this up, the entire exponent becomes negative, not just the x. But then it's an exponent on something you're taking the log of. You can bring that down out front. The log of 10 is 1. So negative x plus 1 times 1 would be negative x plus 1. If you bring this one up, it makes the 3x negative and the 2 negative. The whole exponent becomes negative if you switch his side of the fraction. Then he's an exponent on something you're taking the log of, so the exponent can come down out front. And for, I think, at least the third time already today, natural log of b is 1, because e to the first gives you e. So negative 3x minus 2 times 1 would be negative 3x minus 2. So same log properties. I'm just showing you to be careful about switching that exponent sign. All right, we are just about finished here, where we can move on and actually practice a few out of the worksheet, and you can see more of what will be expected of you. Okay, so graphing logarithmic functions. Again, log base 3 to the x, log base 5 to the x, log base e to the x are the inverses of 3 to the x, 5 to the x, and e to the x. Well, 3 to the x, 5 to the x, and e to the x all basically look the same. So their inverses are all basically going to look the same too. Base 10 also. They will all have an x-intercept at 1. They all have a domain of 0 to infinity. All that changes is how quickly they go up and how quickly they hug this y-axis. But just at a glance, they all basically are very, very similar. So. Okay, so if you needed to know vertical asymptotes, if there's no transformations, just like this one, you can see this one is at x equals 0. But if you did a graph and shifted it left 4, that's going to move the vertical asymptote left 4 also. Okay, the two I'm concerned about are these two, because I don't know that you practice these properties too much, or if you saw them at all in Algebra 2. Okay, so log base 3 to the x is going to look like this, because all logarithm graphs without transformations are going to look like that. Multiplying the x by a negative only flips it over the y-axis. You should have known that for today's quiz. So this is what log of negative x looks like. The part that I'm concerned about, because you guys just unfortunately haven't practiced it much, is when you add 4 to x, you're used to going left 4. But if you're also flipping it over the y-axis, those rules switch. So this is actually right 4. The reason why it works this way, and you probably should add this to your notes, this negative looks like it's just going to the x, but the negative is actually going to both of those. So that's why it is right 4. So the vertical asymptote would be at x equals 0. If you flip it over the y-axis, it's still at x equals 0. But then if you shift your graph right 4, it's going to move to x equals 4. It's going to move along with the graph. So same thing here. Natural log of x would have a vertical asymptote at x equals 0. If you flip him over the y-axis, it's still going to be at x equals 0. Adding 7 to x normally means going left 7, but this negative actually goes to the x and a negative 7, so this is actually right 7. That's opposite of what you usually use. So if that is right 7 compared to this, then his vertical asymptote is going to be right 7 compared to it as well. Again, I know that you guys don't see that much in Algebra 2, if at all, but when you flip over the y-axis, the rules for left and right transformations do switch. All right, and finally, I need to point out one more thing to you so that you can be checking this as we go along. And that is, some numbers don't make sense to take the log of. If we just think of the log graph for a second before we solve these. If I ask you what's the domain of this, you should say 0 to infinity. And the reason why it seems like math classes are obsessed with domain is it means these are the numbers that make sense to plug into this. You can't take the log of 0. The log of 0 doesn't exist. It has no value. You also can't take the log of a negative number. It doesn't make sense. There's no exponent on 3 that gives you 0, and there's no exponent on 3 that gives you a negative number. So you should add those words on your notes here. Never take the log of 0 or any negative number. And then I'll show you how to solve these, and I'll show you how this is going to come into play. Okay, so we get way more in depth on solving logarithmic equations in section 3.4, but in this section we give really basic ones. And what I mean by basic is, this side is log base 3, this side is log base 3, so that part's already equal. You just need to make sure that x plus 4 and 2x plus 5 are the same. It's already log base 3 of both sides. You just need to make sure that the insides are the same also. So you could take away an x from both sides, you could take away 5 from both sides, but before you circle this as your answer, you have to make sure this is not extraneous. My reasoning here makes sense, my algebra is correct, my arithmetic is correct, but it may just not solve the original equation. So you have to imagine plugging this in. This would give me log base 3 of 3 equals log base 3 of 3. Those make sense, so this is the correct answer. I can take the log of 3. 3 is a positive number. I just can't take the log of 0, and I can't take the log of a negative number. So there's an example of where it works out. Over here, you could do the same thing. You could say log base 3 and log base 3 are already the same. So I just need to make sure that the insides are also the same. This is a quadratic, and with the quadratic, you should always move everything on one side set equal to 0. Hope that it factors. Worst case, you do quadratic formula. You get 2 answers. You circle those and you move on. You just messed up. Because one or both of these may not actually work. My solving's fine. My reasoning for this equation's fine. My solving these are fine. But when I plug these in, if I plug in negative 3 up here, I would get log base 3 of 9 minus 3 equals log base 3 of 6. Log base 3 of 6 equals log base 3 of 6. That works. I can take the log of a positive number. But when I try to plug in negative 1, I get log base 3 of negative 2 equals log base 3 of negative 2. And while that sounds fine, left side equals the right side, this doesn't make sense. You can't take the log of 0, and you can't take the log of a negative number. There's no exponent on 3 that gives you negative 2. So this guy would be considered extraneous. And the only way, extraneous just means our reasoning was good, our math was good. We just did some step in there that created a fake answer. Doesn't really solve the original problem. and it happens right here. We write it this way so that we can do this in our head, but this step doesn't take into account what your answers can be and what they can't be. So the only way to catch that is to just religiously plug in your answers to check them. If it works, great, but make sure you're taking the log of a positive number. Never the log of 0, never the log of a negative number. That would not work. That either means you have a mistake or that answer is extraneous. Okay, so now to pull all of this together, like we did with section 3.1, we've got worksheet 1 and worksheet 2. The front is worksheet 1, the back is worksheet 2. So I'm going to start repeating myself a little bit, but I'm going to kind of push you in the direction of how I would approach this, and you can just follow along with me. But on the back, worksheet 2, I will be asking you to try that. Okay, and so for the first 12, I'm going to jump around a little bit because I'm going to try to get you to see that some of these properties are just repeats. So question 1, I've got an exponent on something I'm taking the log of. So I will bring the exponent down out front. And log base 2 of 2 is 1, because that's just saying 2 to what power gives you 2. So 7 times 1 gives me 7. The same properties should be used in question 3, because x is an exponent on something you're taking the log of, so the x can come down out front. And for, I don't know, at least the 5th time today, natural log of e is 1, because e to the first gives you e. Same exact thing. They look like different questions, but they're the same two properties. And even question 11 looks to be the same. The 5 can come down out front. Log base 4 of 4 is 1. 5 times 1 is 5. If you have an exponent on something that you're taking the log of, most of the time you just want to bring that down out front. Okay, question 2. This is the property that looks like this. If you have a number to the log and the base is the same number of something, it just comes out to be the something. So 3 to the log base 3 of 8 is just going to be 8. Same property in number 6. E to the log base e of 5 is just going to be 5. Same for question 12. 10 to the log base 10 of 7 is just going to be 7. Almost no thought required, no work required, but you either know that property and can apply it instantly, or you don't. Okay, I think a lot of the others besides number 7 are probably even easier than these two types we looked at. Because again, we need to be able to read this. This is like 5 times 1. This is saying e to what power gives you 1? That would be 0. Anything to the 0 power gives you 1. This is saying 10 to what power gives you 1? So once again 0, because anything to the 0 power gives you 1. This is negative 2 times 1. And this is 10 to what power gives you 10? Again, you could always set those equal to x, switch from logarithmic form to exponential form, and do it that way. But it's really the same thing as what I verbalized. Okay, number 7 is the one that adds an extra little layer here to it. So in this one, it is a repeat, but you have to use an exponent rule first. You could rewrite this as the natural log of e to the negative 2 by exponent rules. And now that negative 2 is an exponent on something you're taking the log of, the negative 2 can come out front. And for the 5,000th time today, natural log of e is 1. Negative 2 times 1 is negative 2. You're going to see that you really want to memorize that the natural log of e is 1, because you don't want to have to ask yourself that many times. You're going to use it too much. So even though there's 12 questions there, I repeated pretty much the same 3 or 4 properties. So before you forget, you should probably circle the ones that you thought were the hardest, just so when you look back at this, you know which ones deserve more of your attention than the rest. So I will pause for a second before I go into the next section. Okay, the middle section is some solving equations, but again, these are all pretty basic ones. We will do much more difficult ones when we get to section 3.4 after spring break. So I look at this and I know what this is equal to. Log base 6 of 6 is just 1 because it's saying 6 to what power gives you 6. And then you are left with an algebra 1 problem. Add the 1, divide both sides by 3. This is a property we talked about in the top 12 questions. It's actually the same as the property we used in 12. 7 to the log base 7 of 8 is just 8. And then that leaves you something that you can do in your head, only because it's a nice whole number. 2 to the third gives you 8. Not 2 times what gives you 8, but how many times do you multiply 2 by itself to get 8? Over here, we've got natural log of some stuff equals natural log of some stuff. So for these to be equal, the stuff needs to be equal. So we could subtract 3x's from both sides and add 6 to both sides. Just make sure that this is not extraneous. If I plug this in, I get the natural log of 18 equals the natural log of 18. I can do the natural log of 18 because 18 is a positive number. I only can't do the log of 0, and I can't do the log of a negative. Okay, same idea with 16. This is log base 2 of some stuff. This is log base 2 of some stuff. So I only have to worry about the stuff being the same. Divide both sides by 3. And you get 1/6. Plug it in to check and plug it in to make sure it's not extraneous. But it works out fine. Okay, what do you think the answer should be for 18? Should just be 3. Log base 10, log base 10. Make sure 2x equals 6, so x would be 3. Okay, I skipped 17 because this is a challenging one in this little section because it is one you can do by hand, but it does not come out to a nice whole number. So let's talk about a good strategy for this one. Well, first off, we should have an idea of what the answer could be. 8 to the first is only 8. I need it to be 16. 8 squared would be 64, which is way more than 16. So I know my answer is somewhere between 1 and 2, which tells me that my answer is going to be a fraction. If it was a really strange decimal, then it wouldn't be a no calculator question. So what I would do, or the best approach that I've ever seen for this, is to do this in 2 steps. We need to take 8 to some power, and then we'll raise that to some power to get it to 16. We're going to do it in 2 steps. So the first thing I would raise it to is something that's going to make this smaller. So if I raise it to a half, that's like square root. But the square root of 8 doesn't come out to a nice whole number. If I raise it to a third, that's like a cube root. And the cube root of 8 is 2. Then I can reset and say 2 to what power gives me 16, and that would be to the 4th. So I really want to raise it to a third and to a 4th, which is where the answer 4/3 comes from. It's between 1 and 2. It does a cube root and it does to the 4th. Or it raises it to the 4th and then does the cube root. But raising it to the 4th gives you a really big number. You probably can't do that without a calculator. But again, I just lowered it by doing square root or cube root, whatever, just gave me a nice whole number. And then once I got the base down to 2, then I could think about what else I could raise it by to get to 16. So these two end up getting multiplied. Those are hard to do without splitting them into multiple steps. Okay, and then finally, the last part is the graphing part. So we will ask you to tell us about inverses. If this is a function, his inverse would be log base 2 to the x. And why you should want to know that anyway is that if you have to graph this and or answer a bunch of questions about this, you should really start off with 2 to the x. Realize that log base 2 to the x is his inverse. So take all the points you knew about from 2 to the x. Switch x and y, and that's how you can discover what log base 2 to the x looks like with a few specific points without having to learn anything else new. And then you can worry about the transformations. Looks like we're adding a +4 to x, which would be left 4. So take all the points you were sure about, shift them left 4. And everything's going to shift left 4. Vertical asymptote shifting left 4, the domain shifting left 4. But that's the most appropriate way to figure out what that graph looks like. Now that I've got the graph in front of me, I can describe the domain, -4 on the left, infinity on the right. I can describe the range. He goes down forever and up forever. Now granted, he does go up slow to the right, but he does keep going up to the right. The asymptote is now right here at x equals -4. Where exponential graphs had horizontal asymptote, logarithmic graphs will have vertical asymptotes. His x-intercept is -3, and I'm sure about that point. That was one of the points that I had kept up with here, and I shifted it left 4, so I'm sure about this one. The y-intercept looks to be at 2, but I'm not 100% sure about that one. So I will take a second and say, what is y when x equals 0? 0 plus 4 is 4, and log base 2 of 4 is 2. So it looked like it was going through 2, but I didn't know if that was just a coincidence. You can still solve it algebraically. In fact, that's what you've got to, well, actually, I'm 100% sure about this point because it was just moved from this point. 4, 3 is also a point, but you could still check it. Plugging in 4 for x gives you y equals log base 2 of 8, which just means 2 to what power gives you 8, and that would be 3, consistent with the graph. Sometimes you have to do it algebraically, but sometimes it's also good just as a check, as a comparison. Okay, so again, I know all that's pretty quick there, but you should feel familiar with some of it. So the back page is similar to worksheet 1. So you guys still have 10 minutes in class, but between now and Wednesday, I need you to try that worksheet 2 on the back and check your answers. So if there is anything you need to get clarified, you will know what that is. So feel free to use these 10 minutes on that. But I will give you a chance to ask questions from worksheet 2, the back, on Wednesday. Also, just a reminder, we do have Atlas testing tomorrow. It's not an all-day thing like the ACT, but your advisor should mention that to you. There's a good chance you may not have advisory in the same spot tomorrow. And I'm only pointing that out to you because it does kind of break up your routine for the week. And worksheet 2 shouldn't take you a long time for homework, but it will take you a few minutes. So